Hey everyone, my name is Gabe. I think a lot of you know me. I'm going to be talking to you about networking. It's mostly an introduction to computer networking, but then the sort of second half is going to apply it to CloudFoundry concepts. So if you're interested in that stuff, you might find it valuable. There's a lot of jargon in the networking field, and part of the goal of this talk is to introduce you to the jargon words and connect them to like concepts that are actually meaningful. So interrupt me if you hear me like use a jargon word that I haven't defined yet, because I'm going to try to go through this stuff in a way that it's kind of educational. The other sort of caveat is networking is like this vast field. I've been working in this space for a couple of years, but there's probably a lot that I don't know. There might be a few things in here that are just flat out wrong, and if you happen to catch one of those, also raise your hand. Otherwise, I'm totally open to getting questions in the middle of the talk, but I'm going to go through this at a bit of a pace because there's a lot of material. So the outline of the talk is basically we're going to start with the networking layers, the layers of the networking stack, and then we're going to apply those concepts to CloudFoundry, to the boxes and lines of how it works. And if there's time at the end, which there may be, I'll try to go over some like debugging tools you can use to diagnose network problems and understand what's going on when you have networking issues. But there's a lot we're not going to talk about. We're not going to really go into details at all. There's also a whole bunch of interesting networking subjects that I wish we could talk about, but we don't have time for. So getting right into it, networking layers. So like I said, there's a lot of jargon. There are like these two models for networking discussions for terms. One was developed by the telephone industry in the 70s and 80s called the OSI model. It has 7 layers that are numbered. There's this other model called TCP/IP that was developed by the US and UK militaries. It has 4 layers that are named. And networking gurus and people will like use these terms interchangeably. They'll switch between these two models in mid-sentence, and you'll get confused about what they're talking about. And so part of the goal of this talk is to like get you familiar with both models, both sets of terms, so that you can understand the concepts that are being spoken about. So I'm going to use both terms, and I'm going to use them interchangeably, but I'm going to try to let you see both of them. So getting right into it, layer 1. So you've got some awesome computer equipment from like the early 90s, and you've plugged it in to this like networking hub. This is like $20,000 worth of networking equipment, or computer equipment from back then. And so now you have this like these 2 physical networking connections. This is your basic fundamental physical layer of the network. So if you were to measure the voltage on one of these wires that was going between the computer and the networking hub, you'd see that over time the voltages go up and down, and that was encoding digital bits, right? And then if you were to plug in like another computer that you've upgraded, now you have wireless, and you plug that into your network, now you have a couple more physical links. And so this is the physical layer of the network. This is layer 1. And it's pretty straightforward. The message is just bits. And the medium might be a number of different things. It might be voltages on the wire. It might be radio waves. It might be photons going through a fiber optic. And there is a lot that's missing from layer 1. We're not talking about how to forward data across more than one device. There's no concept of addressing in this layer. And there's no reliability at all. So these are all motivations for going higher in the networking stack to address some of these issues that aren't addressed with the physical layer of the network. So we go to layer 2. So layer 2 starts with the bits that we got out of layer 1, and it assigns meanings to those bits. It says, let's take this stream of bits and cut it up into segments and say this set of bits means this thing, and this other set of bits means this other thing. And when you do that and you reassemble that set of bits, you end up with this thing called an Ethernet frame. And the Ethernet frame has a source address and a destination address, and it has a payload of data that it's carrying along with it. Now, there's this other thing called an Ethernet packet, which is almost the exact same thing as an Ethernet frame, but it has a little bit more data. There's a header and footer. In practice, people use the term frame and packet interchangeably, and I'm going to do that here. And there's going to be other terms that we hear later that are also basically the same thing as packet. They all mean the same thing. So layer 2, it's called the data link layer. The message is this Ethernet frame, and the medium is the bit stream that was provided to us by layer 1. And what's cool about this is that we made this homogeneous network where there's Ethernet everywhere, despite the fact that the physical connections between the links might be heterogeneous. You might have radio waves in some places, photons in other places, voltages elsewhere. A few things that are important about layer 2. There's a maximum frame size, the biggest message you can send at a time, called the MTU. Standard sizes are 1,500 bytes. You might see bigger ones. Frames that are larger than this maximum size will get dropped by the layer 2 networking equipment. So you can't send messages bigger than this. And this will require higher layers of the networking stack to chunk big messages into smaller pieces in order to send them out over layer 2. You'll see on your computer Ethernet devices that have names that look like this. There's commands you can inspect and modify networking, layer 2 networking devices with. You're probably familiar, if you're an engineer, with this Ethernet address. It's a 6-byte address. It's usually written with hexadecimal notation with colons in between it. It has a whole bunch of other names. So besides being called an Ethernet address, you might hear it called a hardware address, a link layer address, a media access control address. One interesting thing about this address is that it's a serial number. It's not a locator. It doesn't tell you how to find this device on the network. It just tells you who made this device. And that's an important distinction between Ethernet addresses and IP addresses, which we'll talk about later. So how does Ethernet send data? So you've got some computer, and it's going to send an Ethernet frame or packet or whatever you want to call it, and it goes into this networking hub. So this networking hub actually broadcasts the message everywhere. It has a whole bunch of ports on it, and it might just have different different plugs plugged into different ports. And when the Ethernet hub receives a frame, it will flood it out. It'll send it over every single port that it has. And the way that when the frame hits the next device, maybe it hits that access point after that, that will also broadcast the frame over every connection that it knows about. And so you're wondering, like, how does this work? How does this scale? Why does it broadcast? And the basic idea in this sort of old school layer 2 networking system is that computers that are not the destination of that frame are supposed to just ignore the packet. They're supposed to drop it and just pretend like they never saw it. And that idea that gives you this concept of a broadcast domain. It's the set of all computers of all networking devices that are plugged into each other via layer 2 and that can reach each other via broadcast. It's like the sort of closure of everything. This concept also has other names. LAN, local area network. Layer 2 segment is the one you'll hear networking people use a lot. Just segment in general. So if you took this hub on the bottom left and you were to replace it with this fancy new device called a switch, the switch would be an upgrade, okay? And the reason the switch would be an upgrade is because it has memory inside of it. It's not just blindly forwarding every packet that it sees. It actually keeps track of packets that it's seen. It keeps track of where they came from. And so if, as a packet flows through it, the switch will learn, oh, this packet came from this port and it had this source address, so maybe I can affiliate this port with that source address and I can more selectively forward packets going out the switch later on. So if suppose a packet came in from this Macintosh Quadra and came into the switch and it was destined for the SGI machine. If the switch had seen traffic from that SGI machine before, it would know it doesn't have to broadcast that packet. It can just unicast it. It can send it straight to that one computer and not send it anywhere else. And that's the improvement of a switch over a hub, is that it doesn't have to broadcast everywhere, and that's going to reduce the bandwidth, the amount of usage of your network. But if some packet comes in to the switch that's destined for something that the switch hasn't seen before, it has to fall back to the old behavior. It still has to broadcast the frame everywhere. And so that will have the same old behavior as the hub, and it'll eventually get to the right destination. So this question is that comes up is, as you attach more and more things to the network, your broadcast domain gets bigger and bigger. And the switches will help you reduce the amount of network traffic of like flooding frames that aren't even necessary. But the switch memory has to grow linearly with the number of nodes in the network. So this does not scale. You can't build internet scale networks this way, because each switch would have to have gigabytes or maybe terabytes worth of memory inside of them. And so this is the motivation for segmenting the network, cutting it up into smaller layer 2 broadcast domains, and then doing routing between them. And that's the motivation for layer 3, but we'll get to that in a second. So what's missing from layer 2, this routing across segments. We haven't addressed any way of providing large messages or streams of data, and there's still no reliability yet. So we're going to push some of the solutions to those problems further up the networking stack. All right, questions so far? Yeah.
Subnet? Is that subnet the lane?
Good catch. We'll get to subnet in just a moment. Okay. Have I used the word subnet yet?
Yeah.
Good. Okay. Yeah. Yeah. This talk is going to focus on the modern internet networking stack, which is, HTTP, TCP, IP, and Ethernet, and we're going to ignore all the other layer 2 mechanisms. Anything else? Okay, cool. So layer 3. Layer 3 is the IP networking addressing layer. There's a lot of stuff here. We'll get through this stuff going right into it. Let's start with the Ethernet frame. So we saw this before. It has a source and destination address, and it has this big data payload. What we do as we build these higher layers of the networking stack is we take the data payload from the lower layer and we stick something into it that has more structure. Okay? So we're going to take that and we're going to call that an IP packet. And that IP packet is living inside of the Ethernet packet. And in fact, that IP packet has its own source and destination addresses, which are now IP addresses. And then the remainder of the packet is the IP data payload. And you're going to see this kind of pattern continue as we go through the talk. So these IP addresses, what are they? You've probably seen them before. They're 4 bytes long. They're usually written in dotted decimal notation. There's about 4 billion possible ones in IP version 4. There's this other thing called IP version 6 that has a much larger address range. It's the future, but we're not there yet, and I'm not going to talk about it really at all today. IP addresses, you can make a range of IP addresses, and that's what a subnet is. A subnet is a fancy term for a range of IP addresses, and when you write out the address in binary, and you write out the address of the beginning of the range and the end of the range in binary, you'll see that the high bits in binary are the same at both the start and the end of the range. But the low bits will be all zeros and maybe all ones. And that's the sort of key to a more compact notation. So with this, we can take the shared bits that are in common, and we can write the same subnet, the same IP address range, in what's called the CIDR notation, which starts with the base address and then puts a 0 at the end, and then puts this /24. And the /24 is called the subnet prefix length, and it's basically telling you how many bits are in common between the start of the range and the end of the range. And this is a compact notation for talking about like blocks of IP addresses. So just to sort of continue this, if you wanted to reverse, go from a CIDR notation of a subnet back down to a range of IP addresses, you'd start with the base. The /27 tells you these bits are in common, and then you 0 out the bottom and you 1 out the bottom, the start and end, and that'll give you this final address range. So this is great. This is a nice little math lesson. Why do we care, right? Like, why are subnets even a thing at all? And the reason is going back to this diagram from before. So we had this big layer 2 network. We were like, this is too big. We want to segment it into smaller networks. And so what we're going to do is we're going to have distinct layer 2 networks, and we're going to assign each layer 2 network to be an IP subnet. And that's the correspondence. So usually the case is that a layer 2 segment is an IP subnet, and vice versa. And then we have this question of how do we move packets between them. We're going to move IP packets between them, not layer 2 packets. So just to sort of make this real, imagine you put this IP subnet on this layer 2 segment and that IP subnet on that layer 2 segment and so on. And then you could put these little blue dots between them, which are like IP routers. And the routers can route IP packets between the different subnets. So what's this router? This router is one network device that's attached to many segments. Okay, and the router will forward IP packets, that inner blue thing, but it won't forward layer 2 packets. It won't forward Ethernet frames. And it won't forward layer 2 broadcasts. And that's the difference between like a switch and a router. So this router, I mean, it's just a networking device. It has some ports on it. It has some like Ethernet cables plugged into those ports. The important thing is that the router has a different IP address on every subnet that it's attached to. So depending on which subnet you're in, if you're trying to talk to the router, you'll use an IP address that's meaningful within that subnet, and the router actually has like these multiple identities. So that allows, like with this in hand, we can now talk about the packet's journey, going from computer A to computer B. We're going to like figure out how this works. So we'll start with this diagram of the IP packet inside the Ethernet frame, and I'm going to represent it a little bit more compactly so we can watch this change over time. The same idea. So let's start with this packet, and it's at computer A, and computer A wants to send a message to computer B. So computer A knows its own source IP address, and it knows the destination IP address of computer B that it wants to talk to. How it knows the destination IP address, we're not going to talk about now. But let's just say it knows the destination IP address. And because it's computer A, it knows its own Ethernet address too. So we filled in those 3 fields at the top right. But the destination Ethernet address is not known yet. So computer A needs to figure out what that destination Ethernet address is before it can send this packet out. So how does it do this? it uses this. It consults this local state, this local configuration on the computer called the forwarding table. The forwarding table is just a list of entries which say if you're trying to go to a particular destination subnet, how do you get there? You might go through a particular router. And so this is a correspondence of which router should I use to get to which subnet. And depending on how complicated your local network configuration is, this table might be smaller or bigger. So this table lets us answer the question, okay, we're trying to get to this destination IP address 10.10.9.9. That happens to fall within the particular row at the bottom. And that means we should use the router 192.168.0.1. And so that means, okay, we know the router that we're trying to send this packet through, but it still hasn't actually answered the question of what's the destination Ethernet address that we should attach to this packet when we send it out. So to get that, we're going to need to get the router's Ethernet address. We're going to need to use this thing called ARP, the Address Resolution Protocol. So ARP is really, really simple. It's a question that A sends out by broadcast at layer 2 in a particular format. It says, who has this destination IP address? Please tell me. And it makes this packet in the form of a question, and it broadcasts it out over layer 2 network. And it goes out over the network, and it finally reaches the router, which is going to be able to answer this question, because it is that destination IP. And it says, it makes a response packet that says, I am 192.168.0.1, and this is my Ethernet address. And it builds a layer 2 packet of that form, and it sends that back out over the network. And if finally that reaches computer A, and now computer A is able to answer its question. And so it's able to fill in the destination Ethernet address to attach to this packet. And now it has a complete Ethernet packet with a complete IP packet inside of it, and it can actually send this out over the network. And this all happens like in a matter of milliseconds, right? So we have this fully formed packet, and we're going to watch it travel. So it goes from computer A over this layer 2 network, and it's maybe getting broadcast and sort of duplicated and flooded over this network, but eventually a copy of it makes it to the router. So the copy of it makes it to the router, and the router strips away the layer 2, the outer frame, and throws it away and just keeps the layer 3, the IP thing in the middle, right? And now it has to make a routing decision. It's got a destination IP address, and the router is supposed to route this packet to that destination IP address. How is it going to get there? So the router, we go into the router and we find it has its own sort of forwarding table that looks like the one that the computer has. And it has this table that says for a particular destination site or address, what Ethernet device should I send this packet out of? And so in this particular case, it matches this rule at the bottom. And so that's going to match ETH0, which is the one at the top. And so now the router knows where to send this IP packet. So it wants to send this IP packet out. But the router now sort of faces the same problem that the computer A faced at the beginning, which is I need to send this packet out over a layer 2 network that I'm attached to. I know my own IP address and my own Ethernet address, but I don't know the destination Ethernet address. So the router now has to repeat the same process of doing this address resolution protocol that the computer A did a moment ago. So it's going to go through this process, and it's going to ask who has this destination Ethernet address, or sorry, this destination IP address, and then it's going to get a response from B, and then that response is going to come back, and it's going to be able to finally fill in the destination Ethernet address of this frame. So now the router has a fully formed Ethernet packet that it can send out over this network, and then it travels over the network, and then that finally makes it to computer B. So that's a packet's journey at layer 3. That's the IP packet's journey. This is probably a good place to pause and ask questions. Yeah. Yes, the ARP responses get cached. That's totally key, and it happens most of the time. Most of the time, it's a cache hit, and so it goes really quickly. Yeah.
So does an ARP response through a hub to a machine that didn't make the ARP request get cached on that machine?
So a hub is a layer 2 forwarding device. It broadcasts everything that it sees, and it doesn't change any of the addresses in the packets. So the fact that it went through a hub has no relation to whether or not the ARP message is cached or not.
Sure, but I guess what I'm really asking is something that gets a broadcast that's not intended for cached.
Okay, yeah, that's a good question. So computers will often, the operating system will often cache ARP replies that it sees, even though it didn't solicit those replies, as a way of sort of building up its own internal forwarding table without having to make the requests. That can sometimes lead to problems on cloud platforms where IP addresses change rapidly. And so there's a whole class of problems that can occur because of ARP caches being stale. But yes, that's totally a thing that happens. Yeah. The process that I described for this router would just repeat. So the destination, essentially, this router would have an entry in its table that says if you're trying to get to this distant network, the way to get there is to take a first hop or a next hop that goes through this other router that I do know about. So generally, a particular router only needs to know about the subnets that it's connected to, and then the next hop routers that might be immediately adjacent. That's a good question. But part of the advantage there is that the router doesn't have to know the state of the entire internet. It can just know the state of itself and its local neighbors. And if everyone knows about their neighbors, then you can generally route an IP packet towards the right destination. Yeah. Yeah, we'll get to that. Multiple paths we'll get to. Basically, there are multiple paths is the short answer. Yeah, that happens. So summarizing layer 3, it's called the network layer sometimes, or the IP layer. Did you have a question? Okay. So the message is the IP packet, and the medium is the Ethernet frame that was provided by layer 2, right? And it's called the network layer. It enables large-scale networks, and one of the ways it does this is by having tiers of subnets, bigger ones encompassing lots of smaller ones, which might encompass lots of even smaller ones. And so you can cut the subnets up in this way, and you can have this big tree. And ideally, IP address space would be segmented in this way, and networks that are physically near each other in the real world would have IP address ranges that are near each other in IP address space. And then you could have like, you know, the router for the Santa Monica area that was like connected upstream to the router for the California area, and packets would have like a very short number of hops that they have to take to get to the right destination. In fact, things are really messy, right? And in fact, the real world, you might have two networks that are like physically adjacent to each other but have completely different IP addresses, and that's just the way it is. And then as a result, routing tables have to be kind of large in order to accommodate for that complexity. But that's the idea. Some address blocks that you may have seen if you're a developer, these are like private addresses that get reused over and over again. The top one is like the most common thing for home networks, like home Wi-Fi networks. But there's a bunch of them that are basically reserved. You can use them yourself as long as you don't leak those addresses onto the public internet. So as long as they stay behind sort of a private network, you're okay. Multiple paths. It's a thing. IP packets can take multiple paths. And as a result, packets that are sent in order, A, B, C, D, will not necessarily arrive in the same order that they were sent. And so it is up to the recipient to sort of understand somehow how to reassemble packets in the correct order if they want a message to go across the network that's larger than any one particular packet. We'll come back to that when we talk about layer 4. One more thing. Is that clock right? There's no way that clock is right. OK, it's 1 o'clock. We're good. IP fragmentation. So suppose you do try to send like a big packet, and suppose you form a packet that's like big, and it's actually big enough. It's not too big for the first network, right? So it's able to travel through the big network that you're attached to, and then it gets to a first router, and then the router needs to forward it across the next network that maybe has a smaller MTU than the packet. So then this router has to fragment the packet. It has to cut it up into little segments and then send them one at a time through this smaller network. And then when they get to the end, they'll like be reassembled by the destination. They'll see the fragments, and the destination will understand that it's supposed to squash them back together. This is really great. In theory, it happens in routers, and a lot of routers don't know how to handle it. They don't know how to fragment packets. They don't know how to handle fragmented packets that they see. A lot of routers will just drop fragmented IP packets. It sucks. And so as a result, you can't really rely on fragmentation working. And in fact, if you do get fragmentation in your packets, it will probably cause problems. This is something we've seen relatively recently. I think in the last 6 months, there was a hang in the Linux kernel when it encountered fragmented IP packets. Really bad stuff. So layer 4 tries to mitigate this by doing chunking at the source side, and we'll talk about that a little bit later. But just be aware, if you're having networking problems, if you see stuff with MTUs, this is part of the issue. So to summarize layer 2 and 3, because there's a lot here, layer 2 is about broadcasting packets to get them where they're supposed to go. Layer 3 uses ARP and routing to forward IP packets around. I mentioned this earlier, the address semantics. Layer 2 addresses are totally unstructured. They're like a serial number. It tells you who made the device. It doesn't tell you anything about where it is on the network. The layer 3 address is this routable locator. It tells you how to find the address on the network. If you can get your router to forward a packet a little bit closer to that destination, it will eventually get there through repetition of IP routing. So what's missing from layer 3? Still haven't addressed large messages. The fragmentation story is kind of broken. And reliability and in-order delivery of messages hasn't been addressed yet with layer 3. So those are all motivations. Oh yeah, and connections. The whole concept of like persistent long-lived connections, in which there might be many for a particular application, or many connections on one computer connecting to another one, haven't addressed that either. So these are all things for going to layer 4. more questions before I can move on? Cool. So layer 4, some stuff. We'll get to it. This is the IP packet that we saw before. We're going to do the same process we did before. We're going to take the data payload and we're going to put something inside of it. In this case, we're going to put in this thing called a UDP datagram. This UDP datagram has a source and a destination. This time it's a port number, okay? And then the remainder is a data payload. And so you're asking what's a port? It's a kind of sub-address, but it distinguishes between multiple network-aware applications that are on a single machine. And there's a range of ports. And that's sort of the addressing semantics at layer 4 is just this extra port number. And so what is UDP? It's often called unreliable datagram protocol. It's low latency, it's super simple, but it gives you unreliable out of order delivery of messages that have limited length. So it's basically the same thing as IP addressing. And you're actually wondering, like, what's the point of having UDP if I get the same behavior as I do with the layer below it? And the answer is you can program with UDP as an application developer. You can't program with IP as an application developer. And I'll come back to that when we talk about sockets in just a moment. Just a reminder, this multiple paths problem is totally an issue when you use UDP. It doesn't guarantee the order of delivery of packets. That's the motivation for going to TCP. So TCP takes the UDP data structure and basically adds a lot of extra fields, but the one that we care about today is the sequence number. The sequence number tells you what order did the client or the sender of the packets send the packets in. So it'll send a bunch of packets and it'll number them 1, 2, 3, 4. It actually starts at a high number and increments from there. But then that way the receiver of the packets can see them, and even if they arrive out of order, it can rearrange them and sort them by their sequence number and then get a final longer message out of them that's reconstructed from that. I didn't even mention this earlier, but the UDP packet is called a datagram. The TCP packet is called a segment. They're all just packets. More jargon, you'll see it. People just they show off. They segment, whatever. Okay, TCP has this handshake. The client and the server agree on what sequence numbers they should use. They don't start with 1 all the time. They start with high-numbered things. After they've gone through this handshake, then they can exchange data. TCP has this complicated state machine. I'm not going to go into these details at all, but this is how individual ends of the TCP connection keep track of, like, is this connection alive? Like, is the other person listening? Can I send data now, or do I need to wait? Part of what goes on in TCP is when you send a message, it gets acknowledged. And that acknowledgement tells you whether you can continue to send more messages. If you don't get your message acknowledged, maybe the other side dropped and maybe you should slow down, maybe the bandwidth was saturated, something like that. So TCP connections is this term I introduced. It's just a sequence of packets. It's uniquely identified by this 5-tuple. The source, IP and port, the destination, IP and port, and the protocol, just UDP or TCP. Well, I guess in this case, it would just be TCP. But in general, you can think of like a connection at layer 4 as being identified by the protocol. So TCP gives you reliable, in order, unlimited length messages. This is like finally like gets us what we want from a networking standpoint. But the trade-off is that it's higher latency to set up. You have to do this handshake, and it's kind of complex, the protocol is. If you recall this fragmentation story from before, TCP has this concept called a maximum segment size. It will try to chunk your data up on the client side and send them out as individual packets. And so this is an attempt to avoid the fragmentation problem at layer 3. So now we get to talk about how to actually program with this stuff. So this is where sockets come in. So sockets is this abstraction that came out of the BSD operating system back in the 70s or 80s. Despite this complicated looking diagram, it's pretty straightforward. You have a passive side, which is the server. It listens on a port and starts accepting connections. You have an active side, which is the client, and it makes those connections. And then once the connection is established, for each side just sees it like a file on the file system. They can read to it, they can write to it. And this is a great thing for programmers who are accustomed to reading and writing to files. They can read and write to networking sockets the same way. And this is basically how we use networks today. This is how your language runtime uses networks today, is it creates sockets under the hood for you. So servers listen on well-known ports. These are ports that the developers probably are familiar with. You often need like root privileges in order to listen on low-numbered ports. Clients, people often ask, what port does a client use? The answer is some random high-number port. It doesn't matter, because the identity of the client port is not meaningful to the server. And you can figure out what ports your computer might be using by running these commands. So layer 4. Layer 4 is called the transport layer. The message is the TCP connection, or the UDP datagram, the UDP packet. And the medium is this IP packets that we got from layer 3. IP stands for Internet Protocol, by the way. So there are some interesting things we can do at layer 4. One of them is called a proxy. So a proxy is a thing that acts as both a client and as a server. So as a server, it receives connections from something, and then as a client, it initiates another connection to a different downstream destination. And so the result is that it'll sort of effectively change the IP address and port of the packet. So if you sort of step back and you look at it, the packet's source IP and port change as it goes through the proxy. Why would we want to do this? This is valuable because it can do things like add security to a connection. A client can connect to an unsecured proxy that will then secure the connection down for the next hop, the next segment. It can also do things like load balance. If you have a lot of backends, you want to spread the load across them, the proxies can actually intelligently pick one backend, maybe pick the backend that is least loaded, attempt a connection to it, or if one of the backends fails, the proxy can attempt to connect to another one and try to hide some of that grossness from the client who just sees that they're connecting to a proxy. The other interesting thing that happens at layer 4 is actually a combination of layer 4 and layer 3, which is network address translation NAT. There's two kinds of NAT. Source NAT is called masquerade sometimes, and it's rewriting the source address as the packet goes through the SNAT device. This is commonly used on like home Wi-Fi routers, where you'll have a bunch of different computers that are all given a private address on a private network, and then when they try to reach the public internet, they go through this SNAT device, and their source IPs get rewritten to be the public address of the SNAT box. One thing to note about this is that it requires the SNAT box to track connections. It has to keep track of like which connections are going through it, so that when a reply comes back from the public internet, the SNAT device knows which computer on the back end it's supposed to send that reply onto, because they all appear to have the same address when you're outside this SNAT system. The other kind of NAT is destination NAT, DNATing. It's also called port forwarding, and that's just when you rewrite the destination IP and/or port. This is used in CloudFoundry and Kubernetes, and we'll talk about this a little bit more later. So things that are missing from layer 4. Not much, actually. Application semantics, like HTTP or whatever your application is, and then security. And this is the last time I'm going to talk about security at all in this talk. So questions before we move higher on the networking stack? Stuff about layer 3 or 4? Anything so far? Yeah, I know it's a lot of information. OK. So we go from layer 4 to layer 7, of course. And you're like, what happened to layers 5 and 6? And the answer is that like back in the 80s, there were these two different models, and the telephone company guys thought that there was going to be this layer 5 and 6, and they imagined this stuff that just like didn't happen. It just doesn't apply to the modern internet. So all models are wrong. Keep this in mind. And without further interruption, we just move to layer 7, right? Maybe. If you're talking about telephones, maybe they matter. This talk isn't about telephones. Some people will try to shoehorn like SSL in between. They'll say, well, like if you're going to add encryption to your connection, that's kind of a layer 5 concern. But if you like look at the OSI model itself and what it says layer 5 is, it just doesn't match what SSL is. So don't believe people when they tell you SSL is layer 5. It's not. So layer 7, it's called the application layer. And the message is your application data. It's like what you actually care about as a programmer. And the medium is this transport that's provided at layer 4, TCP, sometimes UDP. So an example for UDP is DNS. DNS is like, tell me what the IP address is for some named server on the internet. You send this message out and as a request, and you get a reply back that tells you what IP addresses are associated with that name. That is a layer 7 protocol. The one that we're all familiar with is HTTP. Get me this web page. By the way, this is the host I'm trying to connect to. This host, this is interesting. This is like the key to how CloudFoundry works. And a lot of ingress works on Kubernetes as well. So this thing is interesting because it lets you build this thing called an HTTP reverse proxy, which is also called an L7 router, which is not an L3 router. It's not a layer 3 router. People will often get this confused when they look at like CloudFoundry router component. It's a layer 7 router. So what is this layer 7 router? The colors will give you a hint. It's actually, under the hood, it's a layer 4 proxy with some extra layer 7 intelligence built into it. So what will happen is a request, an HTTP request comes into this thing, and it will look at the host header line that's in the HTTP data, and it will decide based on this host which backend it's supposed to forward to. It might know about many different backends. Each backend has a different name, and it might be able to front for several different backends, and it'll pick the right one based on the host header. And so the other thing that the layer 7 router can do is, as a request goes through it, it can stamp the request with some extra metadata. It can put some data like this was forwarded for some source IP address. It can put that X forwarded for header on it. It can put a request ID on there. And they can do some more interesting stuff that we won't talk about. So that is the summary of layer 7 concepts, and just sort of like that's the end of the layers part of this talk, the terms and concepts. This is everything 1, 2, 3, 4, and 7. And so this is a good time, again, to pause if there are questions before we start talking about how to apply these concepts to CloudFoundry.
So the layer 7 routing is about multiple domain names being serviced by a single host.
Exactly, and about load balancing to those hosts as well. But that's more of a layer 4 concern, right? So yeah.
How does that fit in with scope? How does that fit in with verifying server certificate?
Right. You're asking about something called SNI, which is a way to verify, well, so that a single proxy can front for multiple secured domains. That would be a great topic for Networking 102. Sorry, I don't have any slides about that. I mean, I could talk your ear off about it, but I don't have anything good to say about it now. Basically, there's a built into the SSL protocol, there's a way for the client to ask for a particular server. So that's in the SSL layer, which is kind of below layer 7, but kind of above layer 4. And then the server can decide which certificate to serve based on it. But we should, yeah. Okay, anything else? Okay, so now that's the end of the layers, and we can move on to how to apply this stuff to CloudFoundry. I realize it's been 35 minutes. We don't have a lot of time left. Okay, I'm going to go through this quickly. The end user sees this web browser connecting to a web server, and they don't realize what's going on underneath the hood. There's a couple layers of networks. There's like an infrastructure network. There's an internal network for CloudFoundry. Let's look at this with like layer 7 glasses on, layer 7 tinted glasses, like what's going on under the hood, right? So we see there's actually 2 devices. There's a layer 7 router. There's actually 2 layer 7 routers, and one of them is provided by the IaaS, the infrastructure, like AWS or something, and one of them is provided by CloudFoundry. And they both like do things to the request. So they'll stamp the request with an extra header as the request goes through. And that's the story at layer 7. So at layer 4, moving down the stack, we'll see that, well, these layer 7 routers are actually, they're also layer 4 proxies. We knew that already. There's this extra thing, though, at the end, there's this DNAT device, this port forwarding device. And this is the way that CloudFoundry is able to host multiple application servers on a single cell. The cell is the CloudFoundry term for a container host. It might be running 100 or 200 application instances on it, different applications from different tenants. And so the way this works is that the CloudFoundry router component will connect to the hosting cell on a particular port. And the DNAT system on that cell knows to forward that particular port to a particular container. And so that's going to rewrite the destination port and IP in order to make the connection work. And so when the router connects to a different port, it'll get to a different container. So that's the story with DNAT. And then to go even further down, if we look at this with layer 2 and 3 tinted glasses, then we see there's actually a virtual router on every Diego cell. And this virtual layer 3 router is connected to every single application container, every single app instance that's running on the platform. And it's connected via a dedicated layer 2 segment. There's like a dedicated virtual L2 path between the router and the particular container. And so this is how traffic flows through to your backend web server. Zooming, yeah. There's, yeah, so it's a good question. Actually, someone just asked about this in our Slack channel recently. There's no layer 2 broadcast to or from containers on CloudFoundry. And that's sort of an intentional security mechanism because layer 2 is not really built with security in mind.
So that you're actually
Yeah, the containers can't talk to anything else over layer 2 other than the virtual router that's on the cell that they're hosted on. So this is what the whole network looks like at layer 2 and 3. There's infrastructure connections at virtual layer 2 and virtual layer 3 between the various components. And it's 120. And so I think I'm going to skip the section about container networking because it's just even deeper. Yeah, like basically you've got this story. Well, okay, I'll go over it quickly. So we've got the story. We've got the routers. They're hooked up to each other via this infrastructure network, but the containers aren't going to use this infrastructure network. But suppose you wanted the containers to be able to talk to each other, but you weren't going to allow the containers to reach the infrastructure network. How would you do that? And this is where the team that I used to be on, that's been in this office for a while, built this thing that's called it's a virtual network. This is a common technology. And we put this thing in, and it's called a VXLAN overlay. And yeah, all these disco colors are real. Like, this is all necessary in order to get the effect. But the effect is that there's actually a layer 2 path from this router over to that router. But it's going through this virtualized system. And so you're like wondering, what the hell is this? So okay, this is the cool part. So you've got your UDP packet, and this is like, we're familiar with this, right? And we talked about DNS, and we talked about HTTP as layer 7 protocol. So there's this other layer 7 protocol that I hadn't talked to you about yet, which is called VXLAN. And so it goes into the UDP packet as this data frame, and it adds its own extra little header. But what's cool about VXLAN is that then the VXLAN application data, what's sort of left over, you can put another Ethernet frame inside of it. So now there's this encapsulated Ethernet frame that's sitting inside of the VXLAN frame, which is sitting inside of a UDP packet, which is sitting inside of an IP packet, which is sitting inside of an outer Ethernet frame. This is what a virtual network is, right? This is also called an overlay network, and the overlay is kind of indicative of the layering. So yeah, this is how container networking works on CloudFoundry. Just to go through it, you have your container. It's going to send an IP packet out over the network. And so as the packet travels inside the hosting container host, the Diego cell, it stays as it is. But then when it goes out over the network, it hits this VXLAN tunnel endpoint device. And this is what does the encapsulation. So that IP packet ends up inside of this much larger packet. So just by crossing that VTEP device, the container packet, which was this blue thing in here, ended up stacked inside this much larger thing. The much larger thing is now able to actually traverse the infrastructure network that all the CloudFoundry system components are attached to. So why do we do this? It gives us simplicity for app developers. They get a private network. They don't see anything else, just containers. It gives operators some simplicity because the routers that they're maintaining don't need to know anything about containers at all. The Amazon routers don't need to know about containers. Your data center routers don't need to know anything about containers. It also gives you some security. We can tag application traffic with the application ID of the source, and that lets us do some cool policy enforcement things. So this is the encapsulated data frame thing. The way that security works is it looks at that VXLAN header, and part of the header is this 2-byte tag, and that tag is where we can stamp the application identity of the application that sent this packet out over the network. So then when the packet goes through the VTEP and it acquires this tag, and then the packet traverses the infrastructure network, arrives at the destination, and then the destination VTEP can look at this incoming packet and ask whether this packet is allowed in or not based on what the destination container IP is and this source app tag. So this is where security comes from. I see a question coming from John.
No,
yeah, it's cool stuff. It's really, really cool stuff. So that and then all the encapsulation stuff gets stripped away once the packet goes through the VTEP, lands on the Diego cell, and then it gets delivered to the destination container. And so that's the virtual networking system in CloudFoundry for container networking. And we called it Silk. This is actually a bunch of different technologies that are attached together to do policy enforcement and to hook up the containers to this network. But if you see people on the CloudFoundry team talking about it, this is what they're talking about. OK, this has got to be a good place to stop. It's only 5 minutes left. So let me quit here and ask if there's questions or anything like that. Yeah.
Yeah. So you start off with 1,500 bytes
Mm-hmm.
at the beginning, and then now you're layering another set of. So how much overhead do these headers give the XLM?
Right. So at the end of the day, when you do that encapsulation stuff, it adds about 50 bytes. And so your packets can be 1,450 bytes, and they'll still go over the network. But it's a source of problems. It can be a source of problems for operators. So we did a fair bit of work in the CloudFoundry side of things to tune it all up correctly so that the MTUs that the containers see when they're sending a packet out is 1450 or smaller, and that way the packets will not get fragmented as they flow out over the network. Yeah, Amazon does their own encapsulation. OpenStack does its own encapsulation. So yeah, sometimes depending on where your CloudFoundry is deployed, you might have a couple layers of this stuff going on, and you have to reduce your MTUs accordingly. Yeah, and some people get concerned about performance with this stuff. I honestly haven't heard any of our customers express concern about performance. They're much more concerned about operations. But yeah, if you're trying to do super low latency stuff, then encapsulation might be an issue. Yeah, so I'll put the slides online. There's some more stuff in here about debugging tools for layer 7, at layer 4, 2 and 3. And then there's this glossary up here with like all the terms that I used, definitions. So you can take a look at that stuff. If you want to learn more about container networking or just networking in general, there's some good resources. And again, in the slides, there'll be like links to those things. And also, we have people in this office who understand this stuff really well. Angela gave a great talk for CloudFoundry All Hands, and there's a Slack channel and code and everything like that. So yeah, now I'm actually at the last slide, I promise. Cool. All right, thanks, guys.